Let's just jump right in. Welcome to a very special explainer where we're venturing into this incredible, beautifully crafted paper-cut world. Right there, you can see our main character, a super curious, adventurous little cat. And as we follow this cat through this whimsical layered forest, we're not just going on a standard fairy tale adventure. We're actually diving into some of the most mind-bending mathematical probabilities out there. So stick with me, because by the time we're done, the way you look at everyday logic, yeah, it might just be completely turned upside down.
Okay, so let's set the scene. Once upon a time in the forest of probability, everything looks totally normal on the surface, right? But underneath the leaves and behind the trees, human intuition is constantly getting totally tricked by the magical and honestly unyielding logic of math. In this forest, what feels right in your gut is almost always mathematically wrong. Our cat is about to learn this the hard way, and frankly, so are we.
So before our little feline friend actually bumps into the other forest animals, I've got to ask you guys a direct question. Can your intuition actually beat the hidden rules of mathematics? I really want you to commit to your gut feelings as we go through today's scenarios. When we hit a choice, literally make a mental note of what feels like the obvious answer, because as our cat is about to find out, everyday logic is about to get a serious reality check.
Section 1. 神灵派对的生日谜题, also known as the birthday paradox.
All right, so our curious cat wanders into this super vibrant forest clearing. It's packed with animals, which brings us to our very first challenge. How large does a crowd need for a simple coin flip chance, so 50%, that two animals share the exact same birthday? Now, think about it. With 365 days in a year, your gut is probably screaming that we need a massive crowd, right? But the answer is literally just 23. Yep, 23 animals. If your brain is telling you that's impossible, don't worry, you're definitely not alone. Most of us just assume you'd need, maybe half of 365 to get a 50% chance, but math tells a completely counterintuitive story here. In a group of just 23, it is mathematically more likely than not that two individuals are going to be blowing out their birthday candles on the exact same day.
Now, what's really fascinating about this is how insanely fast this probability scales up. At exactly 23 animals, we cross that 50% threshold. It hits 50.7%. But watch what happens if we add just 7 more animals to make it 30. Suddenly, the probability jumps to over 70%. By the time our cat sees 50 animals hanging out at the party, we're at a 97% certainty. And at 60 animals, 99.4%. It's practically guaranteed at that point. The cat's intuition, and let's be real, probably yours too, was just totally off. But the big question is, why?
Well, the visual trick here, and basically the reason our brains get it so wrong, is that we naturally tend to imagine comparing everyone else's birthdays strictly to our own birthday. But wait, that's not the puzzle. We're actually comparing every single animal to every other animal. When you have 23 animals, they actually form 253 unique pairs. That is 253 chances for a match. Mathematically speaking, it's actually way easier to calculate the chance that no one shares a birthday, which is what this formula here shows, and then you just subtract that from 1. So that sheer volume of cross comparisons, that is the secret magical mechanism behind the birthday paradox.
Moving on to Section 2. 狐狸的三个纸箱, the Monty Hall Problem.
So, leaving the birthday party with its mind totally blown, our cat trots deeper into the woods and runs into a very cunning fox who's hosting a high-stakes game. Okay, here's the exact scenario the fox presents. Under one of these 3 cardboard boxes is an amazing prize, but the other 2, completely empty. Our cat, feeling confident, slaps a paw on box number 1. Now the fox, who absolutely knows exactly where the prize is hidden, smiles, reaches over, and pops open box number 3. It's totally empty. Then the fox looks right at the cat and offers a trade. Do you want to keep box 1, or do you want to switch your choice over to box 2? Okay, what does your intuition say the cat should do? Because most people immediately think, well, there are 2 boxes left, so it's a 50-50 chance, it doesn't even matter.
But the crazy thing is, it matters entirely. The deeply counterintuitive logic here is that the fox's inside knowledge completely shifted the conditions of the game. Let's break it down. When the cat first picked, it only had a 1 in 3 chance of being right. That obviously means there was a 2 in 3 chance the prize was in the other 2 boxes. When the fox purposefully eliminates the empty box from that group of 2, well, that 2/3 probability doesn't just vanish into thin air. Nope, it entirely collapses onto that remaining unopened box. So by switching, the cat literally doubles its chances of winning from roughly 33% to a massive 66%. You absolutely, positively must switch.
And this brilliantly illustrates just how seriously these counterintuitive paradoxes are taken in the real world. Believe it or not, human academics actually publish rigorous studies on this exact dynamic.
This little game between our cat and the fox, it's used all the time in university-level probability and statistics courses to teach conditional probability and how hidden variables completely alter the landscape of a problem. But the funny thing is, even when the math literally proves it on paper, human brains just stubbornly resist the logic of the switch.
Section 3. 猫头鹰的无限树屋 Hilbert's Hotel.
All right, so our cat, having successfully outsmarted the fox, continues on its journey and eventually arrives at this massive, towering treehouse that just extends infinitely right up into the clouds. It's managed by this very calm, wise owl. Now, despite a glowing no vacancy sign, the owl cheerfully offers the cat a bed. But how? Well, the owl relies on this deceptively simple concept pioneered by the mathematician George Cantor called countable infinity. See, unlike a regular human hotel that has a finite set number of rooms, this treehouse thrives on an infinite set. Countable infinity basically means that even though the rooms go on literally forever, you can still list every single one of them, room 1, room 2, room 3, and so on. Because of this orderly structure, boundaries in this part of the forest are completely negotiable. Full simply doesn't mean finished.
Okay, so how exactly does the owl make room for our cat without actually kicking anyone else out? It's all about simple, elegant arithmetic. Let's step through it. The owl politely asks the guest currently in room 1 to just pack up and move to room 2. Then the guest in room 2 moves to room 3, and so on, cascading infinitely upward. Mathematically speaking, every guest in room n simply moves to room n plus 1. And since the hotel is infinite, every single existing guest still has a room. But magically, room 1 is now completely empty and waiting for our cat. In this magical mathematical space, infinity plus 1 simply equals, well, infinity.
Finally, Section 4, 数学的魔法空间, the magic space of math.
So as our cat finally settles into room 1, kind of looking back affectionately at that sprawling paper-cut forest below, a really profound lesson emerges. Everyday physical logic simply doesn't apply to pure probability. The crucial takeaway here is captured so perfectly by this quote. Limits are not always where we think they are. Think about it. In our finite physical world, space runs out, resources diminish, and sure, 23 people seems way too few to share a birthday. But math isn't bound by physical experience. It's an expansive, magical space. I mean, if a fully occupied infinite treehouse can still welcome a tired little cat, then mathematics always has room for one more idea and one more way to totally stretch our minds.
But hey, before we leave the forest entirely, I want to leave you with one final, totally counterintuitive puzzle just to test out your newly leveled up mathematical intuition. Okay, imagine you've got a sack containing 2 coins. One is a perfectly normal fair coin, a head and a tail. But the other is a trick coin. It actually has heads on both sides. You reach in blind, pull out a coin, flip it, and boom, it lands on heads. So what is the probability that the other side of the coin you just flipped is a tail? Your gut is probably going to scream 1/2, but the magical rules of the forest dictate that the answer is actually 1/3. No way, right? Well, I want you to...
Knowledge grows through sharing. What are your thoughts on today's topic? Let me know in the comments below. Don't forget to subscribe as we continue to grow together.